Hi! How could we help developers write programs that are free from SQL injections? Could we help them even when they do not care about security? My name is Judicaël Courant. I'm working at Orange Cyberdefense, and these are questions I often ask to myself when I review real codes which are full of SQL injections. So first, a reminder. What is a SQL injection? Here you have an example of vulnerable code. So the developer just builds a query by concatenating three parts. So the first part is select star from a table where token is equal to quote, and then the second part is the variable, the content of the variable n, and the third part is a quote again. Once he constructed the query, he sends it to the database and gets back a result set of the rows that were found in the database. So why is this vulnerable? Well, n here is supposed to be a single data token, but if you actually pass some data, which is this one, the highlighted one in yellow here, what you get is a statement which is select star from a table where token is equal to x or 1 equals 1, and then you get a double dash, which is the beginning of a comment, so the ending quote here is just ignored. So instead of selecting in your table the rows for which the token was equal to a specific value, you select all rows of your table. So it's a vulnerability. So the essence of injection, as we can see, is that some malicious data altered the code which was supposed to run. In this case, the SQL code which was supposed to run on the server, on the database server. Injections are a well-known plague. They're listed as the first security vulnerability in the top 10 project of the OWASP, and they have been listed as number 1 for years. There are many types of SQL injections. So SQL injection, LDAP injections, common injection, etc. So in this talk, we will focus only on SQL injections. Why? Because they usually have a strong business impact. There are already a lot of kinds of SQL injections, and they're really prevalent, especially in legacy code, and there's no easy way to fix them in legacy code. So why do we want to propose a tool to prevent injection? Well, our motto is that the burden of security should not fall on the shoulders of the developers. They don't have time for security, they don't have the knowledge about security. So security should rely on tools. So the developers should use better tools that provide them better security. So our attempt at building a better tool is called SQL Trees. It's a small proof of concept library. It's about 1,000 lines of Java. It's immune to most injections, and it's immune even when developers don't care at all about security. In order to understand how it works, let's go back to the initial example. So on the left column, what was intended? So what was intended was is a query which just select rows for which the token is equal to some specific value. What happened when a malicious user gave this malicious data, this highlighted malicious data, is that you select all rows of the table. If you look at the abstract syntax tree of the first query here, you can notice that it's quite different from the shape of the second abstract syntax tree. Especially if you look at the where clause here, you can see that the root is labeled with an equals sign, and there the where clause is quite different, and the root is labeled with an or, since it's an or disjunction here. So the main idea we would like to give in this talk is that strings are a very inconvenient data structure. Even if it's the one used for communication with databases, it's not really convenient, and as a result you get vulnerabilities. On the other hand, trees are much more convenient, and they're quite naturally secure against most SQL injections. So our library is built on this idea. It provides an internal domain-specific language for writing SQL queries as abstract syntax trees. The typical usage of our library is that you just import the relevant part of the library, and then you build a query as a tree in prefix notation. So you have select here, it's the root of the tree, and then you have the three subtrees that we saw before. So star for the column to be returned, the table where you want to look for, and then the where clause here. And you just execute this query and get back a result set. The execute method then just compile your tree into a string and calls the standard Java library in order to execute this string. So, of course, the translation has to be done carefully in order not to be vulnerable to injections. So, what does carefully means? Actually, we conjecture that if our translation is faithful, no injection will happen. What do we mean by faithful? Well, the idea is if you have an abstract syntax tree T, you compile it into a string S. If you pass that string S, you should get back the very same syntax tree here. Right? If you do, we say that the translation is faithful, and we claim that if translation is faithful, no injection happens, mostly, and we will support this claim with further examples later. But first, how do we implement this compilation phase? Well, transforming in an abstract syntax tree into a string is quite straightforward, but the delicate part is translating identifiers and literals. So, as for identifiers, we have to make sure first that they have a shape which is the one of an identifier, so we whitelist them through some regular expression, and mostly we require that they contain only alphabetic and numeric characters. And then we have a list of all SQL keywords, which is considered as a blacklist for identifier, and an identifier cannot be equal to a keyword. As for string literals, we have two options. The first option is quite obvious. When there's some dangerous character, such as a quote, we could escape it. All databases propose means to escape dangerous characters, but the problem is that knowing how you must escape dangerous character and which character are dangerous is quite difficult. It's quite error prone, and moreover, it's vendor dependent. You don't escape string the same way when you escape string for an Oracle database, say, or when you escape them for MySQL database. So instead we opted for the second option, which was a bit less obvious, which is to compile our trees to parameterized queries. So parameterized queries are parameterized statements. Parameterized statements are a way in databases to send a query in which you have some placeholders which can be filled later by some values. And the idea is that each string literal will be transformed into a parameter of a parameterized query, and the encoding of string literals is handled by the database driver, so we don't have to wonder how we must escape it. Okay, if we have a look at our first example, how does our library work with this example? So the injection was select star from a table where token is equal to quote and then the injected value x quote or 1 equals 1 double dash quote. If we want to write this kind of query in SQL trees, what you would write is select of star and of ID of a table and of the where clause ec of the identifier token and the string literal n being a Java variable which is of class string. Now what the compiler does is it transforms this tree into select star from a table where token is equal to question mark, the question mark being the placeholder of this parameterized statement, and the parameter which SQL trees will send to the database is the value given by the attacker, and the database handles it. So it's not vulnerable to this injection. A second kind of injection is colon injection. The idea here is that in this query you would like to select over a column which is provided by the user. So you want to select from the table bugs where bug ID is 1, 2, 3, 4. Of course, an attacker would pass here a string specially crafted so that instead of looking for a column from the table bugs, you would select all columns from the table secrets, and then the double dash makes the server ignore the remainder of the query. So how would we write the query using SQL trees? You would write select identifier C, where C is your parameter, ID of bugs, and then the where clause. How is it translated by the compiler? Actually, the compiler will look at the variable C and will notice that it's not a valid identifier, so the query will be rejected, and so SQL trees is not vulnerable to this kind of injection. Another kind of injection is table injection. The principle is quite similar. You want to select a public column from some table where ID is 1, 2, 3, 4, and the attacker provides, instead of a table name, the attacker provides a subquery which will make you select a secret column from some table and rename it as pubcall, so that it will be displayed by the query. If you write this example using SQL trees, you will select, and there you have the variable table, and once again, like for column injection, the content of table, which is highlighted here, is not a valid identifier, so it's rejected by the compiler output. By the way, why don't we try to pass this as a parameter of the parameterized query? Well, the answer is quite simple. Parameterized query don't accept to have table names or identifier more generally as parameters. Parameters for parameterized queries must be values, always. So what are the limitations of our library? First obvious one is that developers have to understand what a tree is. So it might not be such a big deal, but developers generally don't know what trees are. So they have to be taught about trees. The second limitation is that our approach does not prevent two kinds of injection. The first kind is stored procedure injections. So in essence, you could consider they are out of scope since stored procedure injection happen on the server. They are tied to the way the server handles stored procedures. And the second one is like injections. So what are like injections? Here is an example of a like injection. You select all columns from a table where the name is like some pattern. So here the person sign in the pattern means anything. It's a joker character. And the intention of the developer was to look for strings whose prefix was given by the user. Unfortunately, the attacker here replaced did not give a prefix but give a pattern, as the first character here is a person sign. So instead of looking at some prefix in the database, which is quite fast if you have the right index, the database will have to look all string which contains ABC. And if the corresponding index does not exist in the database, it can be much slower. So an attacker might opt to do some denial of service attack by passing such a pattern. If you code this using SQL trees, you would write the query select with argument star the table and the operator like applied to the identifier name and to the literal string built from your parameter plus the person sign. And the compiler output will be a parameterized statement select star from a table where name like question mark, where the parameter is %abc%. So actually the injection succeeds. And once again, we can see that concatenating strings is not a very good idea, is the wrong idea. Right. As a conclusion, our SQL trees library provides a fairly good protection against most SQL injections. The implementation is quite cheap, it's about 1,000 lines of code. We allow dynamic queries and potentially you can access to all SQL in syntax at least once implementation is complete. As a future work, we would like to extend the library and we welcome all contributions in this respect. And another interesting point would be to look at object relational mappers tools. These tools generally don't provide access to all SQL directly. So that's a limitation of these tools from a functional point of view. So generally they provide some plain SQL access, and these accesses can be insecure. So maybe it will be interesting to replace these accesses by accesses to SQL abstract syntax trees in order to make them more secure. Thank you for your attention. Do you have any question?